We're going to move into the second part here. We're going to be talking a bit about quantum gates. So previously we talked a lot about what a quantum bit was and kind of those physical realizations of a quantum bit. Now we are going to divorce ourselves entirely from physics. We're really going to be talking about things using this abstract notation that we've built up. Okay? So let me get my laser pointer out and let's do this. So just as a quick refresh what we had before the break, any two-level system can be thought about as a quantum bit. What I mean by a two-level system is a system that has two mutually exclusive states. So that could be the polarization of a single photon, or that could be the spin state of an electron. These are only two of a large number of examples. How we're going to label this. So we have our two mutually exclusive states, our spin up and our spin down. We're going to denote them as surrounded by this object called a ket, this line with this angled bracket here. To make our lives more generalizable, we're going to label one state as the state 0 and the other state as the state 1. So we can effectively encode binary information where 0 corresponds to state up, spin up, and 1 corresponds to spin down. And we denote these as well using linear algebra as orthogonal unit vectors. So spin up being the x vector, spin y being the y unit vector. This is arbitrary. We just need to find two orthogonal unit vectors. And additionally, in order for these to be two mutually exclusive and distinguishable states, we need to be able to have a measurement that can distinguish them from each other perfectly, which we have in this Z magnet here, which deflects them upward if they're spin up and downward if they're spin down. Okay. Not the whole story though, because we can also have superposition states, such as spin left and spin right, which can be thought about as having a spin up and spin down component. We once again can represent those as a ket. In this case, we're going to call those kets plus and minus. And as a vector, they are represented as superpositions of 50-50 superpositions of spin up and spin down components. And once again, just like the spin up and spin down, it's arbitrary which one we call the 0 and which one we call the 1, just as it's arbitrary which one we write down as a superposition and which one we don't, because there is still a measurement that exists, a magnet with pointed along the x direction that can distinguish these spins perfectly from each other. Okay, we've kind of given spin up and down preferential treatment here. That's arbitrary. We had to pick someone to be the x and y unit vectors to be our logical 0 and 1, but we can equally well encode 0s and 1s in spin left and spin right. So what are some properties of these qubit systems? Now speaking about them from a mathematical point of view, well, each ket has a corresponding bra. We call them a bra. It's equivalent to the conjugate transpose or the dual. The conjugate transpose part is important because we're always going to take the complex conjugate. We're not going to deal with any complex numbers in this particular lecture. But so far all you need to know for this is that basically what you do is you take the ket you have, the little dagger symbolizes that you're taking the complex conjugate. What that means is you take this guy, you flip it around the other way, and it flips column vectors to row vectors. So it takes the transpose of a matrix and the complex conjugate at the same time. So this is another object we can work with. Call it a bra because when you put two of them together, you take bra and ket and we form like a closed set of brackets. This is the kind of thing that doesn't make any sense when someone just says it, but we're going to use it and hopefully it becomes more clear why we're talking about it this way in just a moment. So, okay, distinguishable states. So any property of a good qubit system is that not any property of a good qubit system, but just a fact about qubit systems is that distinguishable states are represented as orthogonal vectors. So if I look at my 0 vector and my 1 vector, so I can find the inner product of them and I can represent that simply using bra-ket notation as 1, 0 in those brackets. So the bra 0 and the ket 1. I look at that, that means I have a row vector 0, 1, a column vector 1, 0. This is one way to take the inner product. I find that those have 0 overlap. I can do that by the matrix math, or I can just think about the projections, thinking about like dot products, and this vector has 0 dot product with this vector. So that is equal to 0. Similarly, the minus and plus states are also distinguishable, and we can see that by noting that their bracket, their inner product, is also equal to 0. So both of them do have spin up and spin down components, but because of this minus sign here, we can think about that as destructive interference, Or we can just think about it as, those are distinguishable states. There's no overlap between them. We can distinguish them perfectly from each other. States are normalized, which can be interpreted as all probabilities must sum to 1. Makes sense when we get to this next rule. The probability of measuring a system in a specific state is found through the absolute value squared of the inner product. And this is called Born's rule. So let's dive into Born's rule just a little bit. So once again, recopied up here. So let's say we have something in the state 0. Could be an electron in the state spin up, could be a polarization state horizontal, could be something in the ground state of a two-level system. Doesn't matter. We have some quantum system in the state 0, and we ask it the question, are you 0 or are you 1? How do we find the probabilities? Well, the probability of finding it in the state 0 is equal to the overlap of the state we have with the state we're measuring, absolute value squared. So the overlap of this unit vector with itself is equal to 1. Square that, you get a 1. So the probability of asking this state the question, the probability that when you ask this state the question, are you 0 or are you 1? The probability of measuring the outcome 0 is 100%. The probability of measuring the outcome 1, well, I look at the overlap of the vector 0 with the vector 1. Those are orthogonal vectors. 0 overlap, 0 probability of measuring the state 0 in measuring the outcome 1 when you have the quantum state 0. But what about if we have a different state? Now we have the superposition state plus, and I still ask it the question, is it 0 or is it 1? I put it into my Z magnet, I put it into a horizontal vertical polarizer. I ask it the question, are you 0 or are you 1? Well, the probability of it being 0, I'm going to calculate as the ket plus bra 0, the overlap of the state I have with the state that I'm measuring. I find that that overlap is 1 over root 2. I take the absolute value squared. The probability that I measure the state plus in the 0 state is equal to 1/2. Same thing if I try to ask what's the probability of measuring this plus state in the 1 state, 50-50. So, we're talking about these. They really are 50-50 superpositions of 0 and 1. There's a 50-50 probability that we measure 0 or 1. But this is not the only question that we can ask our quantum state. What happens if I ask the quantum state plus, are you plus or minus? Those two are distinguishable quantum states. I can design a measurement that will distinguish between those two states, and I find that the probability of it being plus is equal to the overlap of plus with the state plus. That's 100%. The probability of it being minus is equal to the overlap of the state plus with the state minus, absolute value squared, which is equal to 0. So these two here, they describe the action of the Z magnet in the Stern-Gerlach experiment. They describe what happens if I have a Z spin I send into the Z magnet, what happens if I have an X spin and I send it into the Z magnet, and this describes what happens if I have an X spin and I send it into an X magnet. I get a definite answer here. When the state doesn't match the measurement that I'm using, I'm going to see some level of randomness, in this case 50-50. So just flashing this slide again from the last lesson, we have to think about superpositions as relative to the basis in which we're asking a question. 0 and 1 are not superposition states if we ask them the question, are you 0 or 1? But if we ask a 0 or 1 state the question, are you plus or minus, we have to think about them as superpositions of plus and minus. Similarly, a plus and minus state looks like a superposition when we write it down as a vector. But if we ask the question, are you plus or minus, it's a definite answer. We no longer think about it like a superposition. Superposition is relevant to the context of the measurement. Okay, so there's all these different kinds of bases. We talk a lot about what we call the computational basis. We're calling it this because it's this one that distinguishes our 0 state and our 1 state. Once again, 0 and 1 are arbitrary, but we are going to label one specific preferred basis as 0 and 1, and we're going to call that basis the computational basis. We also have really an infinity of superposition bases, including the X basis, which we see here, which we've talked about a lot. There's the Y basis, where instead of being plus 1 and minus 1, it's plus I and minus I. Also a 50-50 superposition of 0 and 1, but with a different complex phase. In general, we can form, like I said, any one of an infinity of possible bases for quantum bits, where one basis state would be represented like this, and the other would be represented like this. This is a general way to generate anything that follows this formula will be an effective basis for describing a quantum bit. So, okay, what's the difference now? So we're going to be talking about quantum computing. What's the difference between quantum computing and classical computing? Well, we can encode binary information in both quantum computing and classical computing. And we can have randomness in both quantum computing and classical computing. We can have a bit that's, 0 or 1. We don't know exactly which one, and we find out which one it is by measuring it. There's some process in between that's like causing it to flip between 0 and 1 or something like that. So what's the big difference? Well, in a classical computer, you can have 0 or you can have 1. So you can have, your coin being heads or your coin being tails. And it could be always heads, it could be always tails. Or it could be 50% of the time heads, 50% of the time tails. So the value is going to be some combination of the probability of it being 0, the probability of it being 1. Okay? So it's somewhere on this line between 0 and 1. In quantum states, we can have the same thing. We have some probability of it being 0, some probability of it being 1. We have that line, but we also kind of inflate around that line because I can ask it different questions. I could ask it, are you 0 or are you 1? Or I could ask it, are you the positive x state or the negative x state, plus or minus? Or are you plus I or minus I? And all of these possible questions, I can't necessarily ask them all. I definitely can't ask them all at the same time. Okay, so I could have something that's very definite in one direction. I can represent that direction as some axis along this sphere. But if I have the wrong state, I'm going to get the wrong information. Effectively what we have here, I'm not going to get too much into the details of the block sphere, but is quantum states exist as, quantum pure states exist as some point on the surface of a sphere. Classical states exist as some point along a line. Effectively, this means the quantum state space is more complex. Okay, and this complexity is exactly what we're going to tap into to find computational advantages. Okay, so far so good? Cool. So now we have our qubits. How do we mess around with them? It's not exactly useful to have a qubit that's, always in the state 0. I can't process information if I can't also manipulate that information. So valid quantum transformations are given by unitary matrices. These are operations that maintain normalization and maintain inner products. So this is the condition we have for a matrix to be unitary. These U's each correspond to a matrix. And remember that this dagger corresponds to the conjugate transpose. The condition is that U dagger U is equal to U dagger is equal to the identity matrix. This little weird one that we hacked into with LaTeX is meant to be the identity matrix. Effectively, these are the operations that make sure quantum states remain valid quantum states. Remember that quantum states have to be normalized. They have to have a distinguishable partner. So we can see that they maintain normalization like this. So if we want to find the inner product of a state with itself, that's equal to psi, and that should always be equal to 1. If we apply the unitary on the state psi, and we apply the unitary the other way on the bra psi, so we apply the unitary on the ket, we apply the conjugate transpose of the unitary on the bra, we find that we now end up with a U dagger U in the middle. That equals the identity. It goes away. So the inner product of psi with psi is equal to the inner product of psi with psi after this unitary matrix. Okay. It also maintains the inner product. If I have the state psi and the state phi, and I'm looking for the inner product between the two of them, it'll calculate it like this. If I apply the same unitary to both, I apply the unitary on the ket psi, the unitary conjugate transpose on the bra psi, it cancels out. The inner product doesn't get altered if I apply the same unitary to both states. So states that were orthogonal remain orthogonal. 0 and 1 can change to different states, but they always maintain their orthogonality. So what are some common quantum gates that we can work with? Well, here's our favorite one. It's the identity matrix. It's the do-nothing matrix. I put any vector here, any two-dimensional vector, and the identity matrix is going to say, hey, cool, you got a two-dimensional vector. Here you go. Here's the same vector back. Does nothing to it. It's the lazy grandson of unitary matrices. It just does nothing. But it's very important. Very good to throw around. Here's another one that actually does something, the X matrix or the quantum knot matrix. So the X matrix looks something like this, 0, 1, 1, 0. If I apply the X matrix to the 0 state, so remember the 0 state is the column vector 1, 0. I throw that in here. 1 times 0 equals 0. 0 times 1 equals 0. 1 times 1 equals 1. 0 times 0 equals 0. I get the vector 0, 1, which is equal to our 1 state. So this matrix represents an operation that flips 0 to 1 and 1 to 0. For polarization, this would be some kind of birefringent optic that rotates horizontal polarization to vertical polarization and vertical polarization to horizontal polarization. In the case of spin, this is something that takes my electron and just flips it upside down. There's another important matrix, the Z matrix or the phase matrix. So 1, 0, 0, minus 1. If I apply the state 0 on here, I get 1 times 1 and everything else is multiplied by 0 at some point or another. So it takes the 0 state and keeps it the 0 state. 0 stays 0. If I instead apply the Z matrix to the 1 state, I get 0 times 1, 1 times 0, 0 times 0, negative 1 times 1. It throws a negative phase in front of the 1 component. So the 1 state stays the 1 state, but picks up a pi phase shift. Okay? 0 and 0 stay, 0 and 1 stay 0 and 1, but one of them picks up a phase shift. Doesn't seem like it does that much, but let's throw in a different state instead. Let's see what happens when I apply the Z matrix to the plus superposition state. Well, that first term here, remember the Z plus superposition state looks like 1, 1. The first part of it gets multiplied by 1, stays the same. The second part of it gets multiplied by negative 1 and picks up that negative phase. So the 1 component of the plus state gets a negative phase. We end up with plus being transformed to minus. Similarly, minus gets transformed to plus. So it doesn't do much in the 0, 1 basis, but is the equivalent of the not matrix in the plus minus basis. Similarly, if we actually look at this matrix, and this part I'll leave for homework, but if you apply the X matrix to the plus state, it leaves it alone. If you apply the X matrix to the minus state, it gives it a negative 1 phase shift. So the X matrix looks like the not matrix in the computational basis, but operates like the phase matrix in the plus minus basis. Okay, all well and good, but how do we switch outside of the basis? So all of these keep our 0, 1 states and our plus minus states in the same basis. So we can use a matrix like this one. This is called the Hadamard matrix. And what it does is it allows us to switch between bases. If I apply the Hadamard on the state 0, then I get the state plus out. If I apply the Hadamard on the state 1, I get the state minus out. So it converts our logical basis, our 0s and 1s, into our X superposition basis, plus and minus. It works the other way too. If I apply the Hadamard on the state plus, I get the state 0 out. If I apply the Hadamard on the state minus, I get the state 1 out. Okay? It's like our basis shifter, which is really useful. Okay, let's think about that. So we want to create a superposition state, but we only have access to spin up states. We can use if we have something that performs the Hadamard matrix, something that kind of rotates our head, rotates the spin, or kind of has to do it in a bit of a weird way, but does that, then we can have something that creates those superposition states. Similarly, if I want to measure in a superposition basis, but I only have access to a 0, 1 measurement, say that I'm actually looking at the ground and excited state of an electron that's trapped in an electron, like a valence electron in an atom, and I'm encoding my information in whether it's the ground or the excited state. And I have a superposition state. I want to know if it's in the state plus. The only way I can measure this usually is to do some kind of laser thing that's going to tell me if it's in the ground or excited state. So I can't figure out if it's in the plus or minus state. But what I can do is I can apply some laser control sequence that is effectively this Hadamard operation. And that's going to take what was the plus state into the 0 state and what was the minus state into the 1 state. So now if I measure whether it's in the ground or excited state, and I see that it's in the ground state, well, I know that it was actually in the plus state before. If I measured in the excited state, then I know that it was in the minus state before. Yeah? Something fancy there. It allows us to switch between bases, which allows us to create superposition states as well as measure superposition states. Okay. We're dealing with 1 qubit so far. Let's expand ourselves a little bit. We're going to be talking about 2-qubit systems, which is really where things start to get interesting. So we're not going to think about it as like, I have one qubit in my hand. Let's think about Alice has a qubit here. She has one electron spin, one polarized photon, whatever you want. Let's say, for example, Alice has a qubit in the state 0. Bob's over here. He has a qubit in the state 1. So we have two separate quantum systems. How do we think about them together? Our next postulate of quantum mechanics is that separate quantum systems are described by the tensor product of the separate individual Hilbert spaces. Hilbert spaces, think about it like a vector space. It's some place where vector rules and inner products and that kind of stuff are obeyed. Don't have to think too much harder about it than that at this moment. So classically, this kind of makes sense. Alice has 0, Bob has 1. If I think about that as, okay, it's 0, 1. It's binary. Instead of having one of 2 options, I now have one of 4 options, 0, 0, 0, 1, 1, 0, and 1, 1. Alice has 0, Bob has 1. That's the option 0, 1. Similarly, just as there were 4 options classically, we now take our two two-dimensional vectors and combine them into one 4-dimensional vector, obeying the rules of something called the tensor product. We're going to get pretty lazy pretty quick with this, and we're just going to take our 0 and our 1 and smush them into one ket that looks like this, 0, 1. And it gives us a new computational basis as well. So this is our new computational basis, and similarly, I can define new superposition bases as well. So 0, 0 is going to be the vector 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1. It did no one any help for me to say that out loud, but it was fun to say. Okay, and we can also think about them as a global state. So psi tensor phi is equal to big psi, because it's a big system. Big system. Okay, we can also represent these as circuits. Okay, so we're going to be using this circuit model to kind of understand just how these operations work. So let's say that Alice and Bob have their qubits, 0, that both start off in the state 0. We now think about this circuit. So this right here is a quantum circuit diagram. Think about the qubit as moving along the circuit and encountering these elements along the way. So here, Bob's qubit hits the Hadamard matrix. That's going to take 0 and transform it into the state plus. Then Alice's qubit hits the X matrix, takes her 0, transforms it to a 1. Bob's qubit hits the Z matrix. It was plus. That transforms it to the state minus. They hit some 2-qubit unitary. Bob is going to measure it. So this measurement is always thought about as in the Z basis, so it tells them if the qubit is in the state 0 or 1. Alice applies a Hadamard and then measures it, so she gets a 0 or 1 out, but that's going to tell her whether the state right here was plus or minus. Okay, so we have like an initial state, single qubit unitaries, 2-qubit unitaries, and measurements in the 0, 1 basis, and we're going to write that down like a circuit. This is one way to kind of write down the order in which different gates happen. At the end of the day, we end up with classical data. Okay, this is that like when we deal with these quantum circuits, we're encoding classical data. We're setting up our state as some string of 0s and 1s. And at the output, we're getting classical data. If you give me an electron at the end of the day, I don't know what to do with it. If you give me a 0 or 1, I can use that information for something. All the quantum stuff, all the superposition stuff, all the interference happens in the middle here. We still have classical input, we still have classical output, and we get some quantum magic happening in the middle here. So some important gates, we have our familiar crew of single qubit unitaries, X, H, Z, they're all buds. And we're also going to need to have 2-qubit unitaries as well. Probably the most important one is the controlled knot, which we'll represent as UC naught. We can think about this as an X gate. So a NOT gate, something that flips from 0 to 1. But basically what's happening is if the control qubit on the top, so this first qubit line here is in the state 0, don't flip, do nothing. If the control qubit is in the state 1, flip the other qubit. So it's the state of one qubit controlling the state of the other qubit. So for example, if I apply the control knot on the state 0, 0, the control is in the state 0, that means don't flip. So 0, 0 stays 0, 0. If I apply it on the state 0, 1, once again, the first qubit, the control qubit, is in the state 0, don't flip. If the state is 1, 0, the control qubit is in the state 1, so it flips 1, 0 to 1, 1. It flips that second qubit on the command of the first qubit. And if it's in the state 1, 1, control qubit in the state 1, flip 1 to 0, 1, 1 goes to 1, 0. The C naught flips the second qubit depending on the state of the first qubit. Okay? So now how do we deal with this when we deal with superpositions? To do that, we're going to take advantage of one of our favorite things about quantum mechanics, and that is the fact that it is a linear theory. If something applies to 0 and 1, then it also applies to superpositions of 0 and 1 if I expand it into its 0 and 1 components. So how does that work? I have this C naught unitary, and I'm applying it to the state plus 0. I don't know what the controls in the state plus. I don't know what to do with that. So what I do is I expand it. I know that the state plus is equal to the state 0 plus 1 divided by the square root of 2. So this is equivalent to 1 over square root to 0 plus 1, tensor the state 0 with the unitary C naught out front. And then if I expand that out, I get 1 over root 2 UC naught 0, 0, 1 over root 2 UC naught 1, 1. So I've taken this plus state here and expanded it into its 0 and its 1 components. Okay? And now, well, we established the rules for the C naught before in the logical basis, so I can apply the unitary on the 0, 0 component and the 1, 0 component. And I find I get the state 0, 0 plus 1, 1. Okay, so we start off with this state here, plus 0, and it's gone to the state 0, 0 plus 1, 1. This state actually has a very special property called entanglement. Okay, what does that mean? It means that the state is no longer separable. So we thought about this plus 0 state as Alice has plus, Bob has 0. Those are two separate states. Alice can measure her state without interfering at all with Bob's state at all. Bob's state is completely independent of Alice's state. But this state right here, if Alice measures the state 0, Bob also measures the state 0. If Alice measures the state 1, Bob also measures the state 1. So Alice's state is correlated with Bob's state. And it turns out that no matter which basis Alice measures in, that's going to determine Bob's state as well. Their correlations extend beyond just the 0, 1 basis. Mathematically, what entanglement means is that an entangled state cannot be written as a tensor product of two separate states. That's all that entanglement means. And this one, if you try to write it in this form as Alice's state tensor Bob's state, not going to be able to do it. So what we can say here is that the C naught, it's a 2-qubit unitary, and it's an entangling operation. It takes this separate state, the state where I can really think about it as Alice's qubit and Bob's qubit, and makes them into an entangled pair. Okay? When we actually kind of build up quantum circuits, depending on the implementation you're using, especially, it can be impractical to have every possible gate available to you. Think about this like in the sense of like digital logic design. So we know that we can, we start learning about digital logic design, we learn about NAND gates, AND gates, NOT gates, OR gates, NOR gates, this whole family of gates. But it's pretty impractical from a machining perspective to be able to build all of those gates. So what we often rely on is something called a universal set. In classical computing, I can build an OR gate, I can build a NOT gate, I can build an AND gate if I just have access to a NAND gate, to a NOT AND gate. If I have a whole bunch of NAND gates, I can build any other gate. That's what we call a universal gate. In quantum mechanics, we have the same thing. We have the same concept, although there's no single universal gate. We need a universal set of gates, and the minimal set corresponds to 3 quantum gates. One example of 3 quantum gates that are universal is the Hadamard matrix, which we talked about before, the C naught matrix, which we talked about before, and this guy here called the T matrix, which is kind of like the Z matrix, but with a different phase here. So it's like the fourth root of the Z matrix. We have this e to the I pi over 4 phase instead. So using these 3 matrices, we can build any other gate. So for example, the swap gate, something that says take Alice's and Bob's qubits and switch them around, can be built with 3 C naught gates. The controlled Z gate, so same idea as the controlled NOT, but instead of controlling whether or not it flips, it controls whether or not to apply a phase, can be built with 2 Hadamards and a C dot. Sometimes these are easy to do. sometimes it's not easy to do. Like, let's look at this gate here. This is the Toffoli gate or the controlled not gate. So 3 qubits, only flip this bottom qubit if both of the above are in the state 1. And we see that it ends up looking something like this using our universal set, where T dagger is actually equivalent to something like 7 T gates in a row. S is equal to 2 T gates in a row. So we've simplified our notation a bit. And even then, it's still a lot of gates. It's an expensive thing to build here. But nonetheless, it is possible. All right, if you want to start playing around with quantum gates, start playing around with these kind of quantum circuits, you can do it. So there's some good simulators out here. This one is run by IBM, their IBM Q initiative. You can find and sign up for an account and start playing with their simulator at this link here. So this is an example of building up that Toffoli matrix, building up that Toffoli gate story using the IBM quantum experience, which you can then run via the cloud on IBM's quantum machines, if you're willing to wait for a little while. Okay, so we now have our mathematical toolbox for working with quantum bits. What can we use it for? So in the next section, we're going to use what we talked about today to actually build an algorithm. We're going to look at something called the Deutsch-Jozsa algorithm. We're going to solve a useless problem, but we're going to show that quantum mechanics can do it better than classical mechanics can. But first, I'm going to get a coffee, and I'm going to encourage you to do the same. We'll see you in the next video. See you there.